Hello, class. I'm here to talk about Chapter 11, the waiting line models, or also known as the queuing theory. I believe the most simple definition of queuing theory would be the mathematical study of waiting lines or queue. As the summary of your book states, let me go over here. Here you go. Um, Waiting line models have been developed to help managers make better decisions concerning the operation of waiting lines. Another thing that I find interesting here, as many of the examples in this chapter show, the most obvious applications of waiting line models are situations in which customers arrive for service, such as at a grocery checkout counter, bank, or restaurant. And but also waiting line models can be applied to many different situations, such as telephone calls waiting for connections, mail orders waiting for processing, machines waiting for repairs, manufacturing jobs waiting to be processed, and money waiting to be spent or invested. What managers attempt to achieve by using the waiting line models? Well, managers want to determine an acceptable waiting time for a customer, or they wanted to think of ways to distract the customer attentions when waiting. And also you can think they might want to inform the customers of the average waiting time so the customer may make the decision whether they wanted to stay or leave. Think about it, Cracker Barrel. I don't know how familiar you are with the restaurant and how they have the little shop right next, connected to the restaurant. So while customers are waiting, they're distracted by looking at several things and buying and candies and all kinds of clothing, all kinds of things you can buy at Cracker Barrel. And also, when you arrive there and then they connect in their little device, their iPads, they do have some kind of waiting line model where they are able to tell you, oh, the wait is about 30 minutes, or the wait is about, well, it really depends. If you show up there on a Mother's Day or a Thanksgiving, you're probably going to wait about an hour and 30 minutes. Otherwise, in normal situation, you would probably expect to wait about 10 to 20 minutes. So this is what waiting line models measure and can help a business. We are not going to be addressing the customer's behavior. There are specific terms for customer behavior, such as when they just wait for a little bit and leave, or when they keep switching lines, which I have posted something on your discussion thread that we call the Murphy's Law. Is usually when we move lines, the other line moves faster. I'm sure you experience that, or at least you think they do. And so many other behaviors that can happen, or customers that don't even get to go into the door just by, driving by and they see a long line, they just leave. So we're not going to be addressing those. We're more is worry about the managerial side of it, uh, how to calculate all this, and then by having these numbers, providing to managers where they can think of alternatives to diminish the time a customer would be waiting. Okay, so we're gonna be going over problem one and problem seven. Problem one is really talking about the structure of a waiting line system, a very basic structure. And then we're also going to address problem seven, which is going to talk about a single server waiting line model right here with Poisson arrivals and exponential service times. Don't think too much about the terms. Again, these are formulas, and once you have defined, uh, the arrival time, the service rate, all you have to do is to plug into these formulas, and then it becomes very easy. So sometimes by looking like this, it looks very ugly, but you see that it's not as bad as it looks. Let's go to problem one right here. It says that this national bank operates a drive-up teller window that allows customers to complete bank transactions without getting out of their cars. On weekday mornings, arrivals to the drive-up teller window occur at random with an arrival rate of 24 customers per hour or zero point 0.4 customers per minute. Right here, they're giving you both. So depending what the question is asking you, we're gonna be using one or the other. Okay, so let's start by right here. The arrival per hour is 24, correct? Customers. And the arrival per minute is zero point 0.4. Well, keep in mind the arrival date is this symbol right here is also called the lambda. It's called lambda. If you see a mu sign, as we like the mean sign as we have seen before, which you will see on problem 7. So if you see the mu sign, that would be your service rate time. Okay, so right now we're just going to be using the lambda. Again, we're just doing the very basic one. It doesn't give you a lot of information, just want to know very basic things. So the first question, so A is asks you what is the mean or expected number of customers that will arrive in a 5-minute period. Again, a 5-minute period. You've been giving already the arrival rate in minutes as well, so you don't need to convert anything like you would probably be doing for problem 7, if I'm not mistaken. Then let's go over here. All we have to do, well, we have 5 minutes, and we know that zero point 0.4 is is the arrival rate. So you know that 2 customers in every 5 minutes arrive. Okay, or a car drives up, but you call it as 2 customers, or you could even say 2 cars, but really we're talking about customers. And then you would be done right here with A. So you have 2 customers in every 5 minutes. There you go. If you see, all I did is to put the equal sign so I don't have to type everything again. You don't have to do it. Sometimes I know I go too fast because I don't intend that you do it exactly like me. Again, use what is best for you. As long as I can see your formula, again, I don't grade any work that don't show me any calculations. So as long as I can see your formulas or your calculations and how you achieve the results, you're fine. Okay, it really doesn't matter. I'm gonna show you 3 different ways to answer part B. So it really doesn't matter which one you prefer. I'm gonna accept it. So if you're not comfortable with Excel, I'm gonna show the first one. Then if you're somehow comfortable with Excel, there's a second way. And then if you are very familiar with Excel, I'm gonna show you a third way. Right here, this formula right here equals to lambda raised to x times this is called the negative exponential distribution. And then right here is going to be lambda divided by x factorial. Or that means x is the number you're giving in factorial. If you do not remember what a factorial means, if I tell you that we have a 5 factorial, all you're gonna do, you're gonna have to multiply 5 times 4 times 3 times 2 times 1. So that means you multiply all the values, you multiply all the values that come before, including the number. So right here, it would be 120. So this was factorial. Excel does have right here a formula. So if you want to do factorial of 5, you get 120 as well. So this is this part right here. So X right here is going to be for 0 customers because, oh, it will help if I read B. Assume that the Poisson probability distribution can be used to describe the arrival process. Use the arrival rate, which is, this is lambda, the arrival rate, in part A, and compute the probabilities that exactly 0, 1, 2, and 3 customers will arrive during a 5-minute period. So all I did is x equals 0, 1, 2, 3, 0, 1, 2, 3, and we're going to be using this arrival rate or lambda. So we have our lambda and we have our x already. Okay, so lambda is always going to be 2. Your factorial x is going to be first is going to be 0, and then it's going to be 1, and then 2, and then 3. And lastly, your negative exponential distribution, I'm going to show you. Right here, one thing you have to remember, any number with an exponential of 0 is equals 1, and 0 factorial is always equals 1. This is going to be for the first one right here. You have to remember that, and you're going to see why. However, if you have a negative exponential distribution with a lambda of 1, for example, do you see right here? Refer to the appendix C on page 817 for values. For example, the negative exponential distribution with a lambda of 1 is equals to 0.3679. How do I know that? Well, let's go to page 817 of your book. How do I go back to there? Oh, here, yes. Okay. So this page right here is showing you all the negative exponential distribution values already with the lambda. So right here you have the lambda, and right here you already have the negative exponential distribution calculated, or the percentage calculated for you. So I just said that a lambda of 1 would be 0.3679 right here. Let's go back. 0.3679. That's how I figured that. Okay. Um, However, we have a lambda of 2, correct? So let's go back to this table and let's look for a lambda of 2. So a lambda of 2.00 is 0.1353. 0.1353. I tried to copy here. I'm not a very big fan of that way that book does. I'm gonna put it here for now. Yeah, it did. Copy. Fine. That's good. I just want you to see why I put this here. So for example, for the first one, with 0 customers arriving, if you substitute all this on this formula, which I have posted here as well, see that's how exactly how I should look. So you're gonna have what? Lambda is what? Is 2. So right here. And then the caret is because in Excel that means raised to x. My x is 0, 0 customers, multiplied by the negative exponential distribution of lambda 2. So right here I will have exponential raised to negative 2. That is my lambda right here, this portion, divided by my x factorial. Remember, x is 0, so my 0 factorial. So I'm really just working with these two numbers, x and lambda, and replace everything here. Okay, so if you do one by one here, on lambda raised to your x value, so you're gonna have what? You're gonna have 2 raised to 0, correct? Which is 1. 0 any number with an exponential of 0 is equals 1, or raised to a value of 0 is equals to 1. Okay, so this is this bar right here. And then we have this value, which I already got it for you over here. Let's suppose that you didn't have that table. You could also do exponential of minus, and then my lambda, which is this portion right here, and then it gives you the same value if you didn't have the table over here. And remember, x factorial, 0 factorial is always equals 0. So if you would use Excel to confirm that, the factorial of 0, it's 1. So now let's put all this together. So we have uh, lambda raised to x, so it's 1, which I'll calculate right here, times, I'm doing the numerator right here, times my negative exponential distribution, my lambda of 2, which is this value over here, or over here, divided by my 0 factorial, which we know is 1, enter, and here you go. And you're going to have the same exactly the same value, because here you multi the numerator, you're multiplying the value by 1 and then divided by 1, so it is own value. So let's go ahead and put it over here, equals to this value. Okay, this is one way to do it, which is seems a long way, but really I just substitute everything. The other way is just to really do it like you see on this formula right here. So, but you got to be very careful with your parentheses. So Excel respect which one is being divided and raised and factorial. So the first one we have a 2, right? Which is your lambda. Raised, I'm doing the same thing, just different way. Raised by x, right? Multiply by, now I have a formula, exponent of a -2, my lambda, divided by a factorial of my x, which you get the same value, just a longer formula. And a third and last way, in simple, but be actually you don't even have to be that familiar with Excel. In I just needed for you to understand where these numbers came from. The last one, you have a formula that it just says Poisson distribution. And what is asking you? First, for the x. And it is asking you for your mean. Your mean is your arrival rate, your lambda. And now is the thing. For the true, if you put a cumulative, it's and you have any values before that, is going to be adding those values. So you want an individual value. So we're just going to do the false. And then you get the same value over here. Okay. Let me format it so I don't have to change um, digits every time. Okay, if you would do the same thing here, which I'm not going to do it because it's a very, let me move the formula, big formula over here. You can do it on your own. For the second one, lambda 2 raised to x1, so that's 2 times the exponential of negative lambda, so 1 times, and then you have the same thing divided by the factorial, divide 2 times 1 is going to, or actually 1, yeah, it's just 1. Let me think. Now it's 2, correct? Because here is going to, oh, yeah, this, okay, again. The bottom here is still going to be remain 1 because 1 factorial is 1 times itself. The top is going to be 2 times this value. 2 because 2 lambda raised to 1 is 2 times this value. So over here, if you would do all that calculation, you really just do 2 times this value. Here we go. If you would put on this formula right here, you're going to have to do 2, which the lambda remains, raised to 1, now x is 1 now, times the same value, you can just go ahead and times this value, okay, divided by the factorial of 1, which is 1, and here you go, you get the same thing. And then also you can go ahead and use the formula, distribution. My x, it's 1. Now we are using 1. My mean is my arrival rate, and my cumulative is false. I don't want to add the value before, and it's about the same. It's a matter of digits where you point it. Okay, and then you can keep doing the rest. Okay, so all I'm gonna do here, I'm gonna freeze my lambda value right here because it's always gonna be the same, and I just wanna Excel when I drag down to update these values over here. Okay, so I'm gonna drag it down, and there we go. Okay, so I'm not gonna complete this because this will be the same values. It's just a longer way. Lastly, what do you want to do? If you want to know for all three, you have two ways. You can either do a sum of all these values, and get a 80.71%. Remember, probabilities are equivalent to percentages. Or another way, which I told you about the true and the false, let me put down here. Now, if I use the formula Poisson distribution for 3 customers with a mean lambda 2, but I want to be accumulative, everything that comes 3 as well before to be included, and you're going to get exactly the same value. So that's why I said be careful with the true and false right here, because the true is going to do accumulative and the false not. So here we go. I showed you another way as well. Well, and which helps us to answer the last one, C. So right here you have B. You're done. And it took a longer than the usual because I want to show you all the details. And for C, delays are expected if more than 3 customers, more than this percentage, arrive during any 5-minute period. Where's the probability that delay occurs with more than 3? Well, if you have 85.71% for 3, for more than 3, you can do 1 minus the total, or equals 1 minus this Poisson distribution, which is the same thing, or 1 minus, and you can put it here, the Poisson distribution of 3 customers. So it's showing 3, 2, 1, and 0. That's what it's doing for you. With the mean or lambda arrival day value of 2, and we want a true because we want to include all the ones before 3, and then you get the same thing. And you would be done. So right here, see, uh, delays are expected. So what is the probability that delays will occur? So which one is that? It's F28, column F28. So I'm going to put here, so it's equals to F28, which is 14, or a 14.29, or a 14.3, or a 14. Any of those answers are acceptable.